Welcome to the 13th session. Today we are going to talk about the non-parametric tests. We'll complete, as you remember, from the last session, we talked about Whitney, but we will revise the post-hoc analysis for Anova test, and then we will move on to the non-parametric tests, to the other three of them. Then we are going to talk about the ROC AUC, as we promised that we are going to work on these stuff. We will use Excel for ROC and AUC, but of course they can be done by SPSS, then meta-analysis by Rahman. Okay. If you remember, those are the parametric tests, and for each one of them, we are going to discuss one of the non-parametric tests. Okay, two sample t-test, Whitney, one-way Anova test, Kruskal-Wallis test, and Wilcoxon for the other two options, the one sample t-test and the bird sample t-test. Okay, it's actually easy to do them, as you know, because there's we do not have multiple assumptions to test before doing them, but of course we have some assumptions. For example, for Whitney test, okay, we are comparing two groups. Okay, if one group has kurtosis and the other group has skewness, the result can't be trusted as when they are both having the same problem. Okay, if they both are right skewed, positively skewed or negatively skewed, okay, or if both are having a problem with kurtosis to the same direction, okay, to the positive kurtosis, for example. Okay, and how do we test for that? We just take the histogram for each one of these groups, and for these histograms we compare them. Okay, so we have assumptions and we need to think about them, but they are so easy to be done, not like chi-square, not like t-test or Anova test. Okay, as you remember the tests for normality. Okay, so do you have any questions before we move on to the training?
No.
No questions?
No.
Anybody's talking? I'm not able to share my other screen. Does anybody know how to solve this problem? Okay.
You disabled that from your first computer, right?
Now it's working. Okay. You see my screen? Is everything okay? Has anybody tried anything we have talked about last session? Okay. How to do the tests for normality? Do you remember? If I want to test the random number for normality. Analyze descriptive statistics, explore. Okay, this is the random number. I take it. Statistics, descriptive. Okay. Plots, normality tests, histogram. We don't need this. Continue. The options. We don't need anything. If I want to test two parts of this variable, like those graduated and not graduated, I will add the graduation here, okay? But now I want to test the whole variable, okay? And here we can see skewness, and we talked about how can we discuss skewness, how to discuss kurtosis. Then we went to the Shapiro-Wilk, and it is significant. When these tests for normality are significant, then I can't assume that this distribution is a normal distribution, okay? As you can see, there is a lot of skewness. Okay, the dots are not hugging the line in the normal QQ plot. They are not like a zigzag on the detrended QQ plot. And here you can see the skewness clearly. Okay, so after that, we talked about we talked about the post-hoc analysis for Anova test. Okay, do you remember how to do it? Analyze descriptive statistics. Is that right?
No, I think we took it from the compare means.
Compare means, one-way Anova. I take the ID, for example, graduation as a factor for distribution. From the post-hoc, I take the 2-key test. Continue. Do we need anything else? Let's take the descriptive and means plot. Okay. I'm sorry, I found out that I'm muted my computer. So has anybody talked about anything? Because like I was asking and I was assuming that nobody has any answer. So was there any answer?
The second time, yes, there was.
Okay. So in here, what do we have? Descriptives, a group, another group, a third group, means, standard deviation, standard error, and so on. Okay, the ID 20 between groups, within groups. Okay, and what we need is the significance. It's not significant, and when we go here, we see the conversion between each two of these groups. Okay, so we have 6 conversions. Okay, and here we can find the significance of each one of those of those comparisons. And here you can find, okay, the difference between semi-graduated and graduated is really big. But for example, I don't think the difference between these 2 points will be significant, or between these 2 points is significant. Okay, so is there any question to me? Okay, as we said, we have a lot of non-parametric tests, non-parametric variables, and we want to do some of the non-parametric tests. Okay, for example, actually we can say that we can apply the non-parametric tests for each one of those, but those are all continuous. Let's just change our target a little bit. For example, let's take those. Do you remember those? Interest, ability, experience, and these stuff? Those were not continuous data, okay? Those were ordinal. Okay, and for ordinal, we do not have the choice to do parametric tests, okay? So what we are going to do is the non-parametric tests, okay? From analyze, okay? Let's assume that I want to compare interests and, okay, let's just take interest, and I want to compare interests between people at the Faculty of Medicine and other faculties, okay? So, does anybody have any clue?
Also, the compare means there were other choices.
From compare means?
No, Mohon.
From the non-parametric test.
Yes.
Okay, non-parametric tests. Okay, we have 2 options, either taking the choice from here or choosing it from here. Okay, we will try them both. Okay, people from Damascus University and non from Damascus University are 2 independent samples. Okay, so I will take these 2 independent samples. Oh, okay. Actually, they are already done. I will take those out. I will add interest. Yeah, for the uni, 0 for other universities and 1 for Damascus University. Come with me is already checked. Okay, I don't want to like go to the table again, but you remember Whitney is used instead of the 2 samples t-test. Okay, for the options I will take descriptives because otherwise SPSS won't give me any other table. Okay, and okay, what do we have? Okay, first they said, okay, for interest we have all the information. For uni we have all the information. Then we compared those on other universities and in Damascus University. Here the comparison is not about the mean, it's about the mean rank, and this number doesn't mean anything to us. Okay, so if we want to take the means, remember that we want to we need to split the file as we said before. Okay, when do we split the file? When we need something like this, I need the descriptive statistics about each one of these 2 groups, okay, without taking anybody out. Okay, so I split according to the uni, and then I click descriptive statistics. Then he will give me the descriptive statistics for the first part, for the zeros, and then for the ones. Okay, so, and here we have the significance. Okay, this significance is 0.4, so it's not significant, and we can say that the 2 groups are not different in their experience, I think. Yeah, interest, in their interest. Okay, is that fine?
Yes, the groups are not different.
Are not different. Okay, is there any other way? Yes, there are. There is another way. I take non-parametric tests. I take from here, as we said last time, we didn't have the time, but now we have. So independent, are we recording? Yeah. Independent samples. Let's take those out. We need the interest. And our groups are based on union. Okay, okay. Let's talk about this window. First, the objectives. Let SPSS decide what it wants to do. Okay, so automatically compare distributions. The fields, I need to select the fields, okay, the groups according to them, and okay, I will tell you something. I will compare everything, all the original data I have, okay, so we see how they appear, okay, and for the setting, automatically it chooses the test, or I can take my Whitney to sample the test. I can click that, and the SPSS will go directly to my test. But I want to let him try his options, and I will see if he chooses my Whitney or another test. Okay. Done.
Okay.
Okay. The result is totally different. Let's read this. Okay, the first line. The distribution of interest is the same across categories of uni. Okay, what does the distribution in here says? If they are not significant, that the distribution is same between the two groups. Is that right?
Yes.
Okay, this is the null hypothesis. Okay, then they did the test. What was the test they did? Independent samples found test. It is the same test I used. Is that right? Okay.
Yes.
Then they put the significance. Okay, why the significance is different from the one we chose in here? Do you see why it is different?
It's not.
Now we entered more.
Actually, there are two ways to calculate the significance, and here they are detailed. Here it is not different. It's different from the first, but not different from the second. Okay, what is the difference in here? Here, it's better to take this significance. Why? Because it's assuming, okay, it's trying to increase the power. How to increase the power? Okay, I assume first that it is a one-tailed test, okay, and I compare from this side. Then I assume, okay, it is a one tail test from this side, and then I take the significance of both of them, okay. This way will increase the power, okay, and this is possible in here in the non-parametric tests. If you remember, in the t-test, we couldn't do that, okay. It's either both ways or one way, okay. So this is not one-tailed, as you can see, one-tailed multiplied by 2. So they applied one tail to both sides, okay. And here they give you the decision: retain the null hypothesis which is there is no difference. Okay, does that seem cooler than the way we used above?
Kind of.
Yeah.
Yes.
Okay, let's take the second. What is the second? If you remember, we took 5 variables. Okay, so for the second one, ability, experience, average, sum, they are all similar between groups. Okay, so those are 2 ways of calculating the p-value, the significance for Mouaz U-test. Okay, let's look at this. This has something special to do, to be done. You can actually click on that line and you will see what will happen. Okay, what happened is not so good. Okay. Where is it? Aha.
Takes time.
No, but it went to the side because I was plugging in the screen before. Okay, here it is. When I clicked, I received this. What is this? This is a histogram for the 2 groups, like flipped to be beside each other. Okay, so this is a histogram for uni 1, and this is a histogram for uni 0. And you can see that they are not different. They have the same skewness. Do you remember that I told you that there is an assumption for Mouaz tests that I have the same distribution? Okay, instead of splitting the file and doing a histogram for each one of them, I can do the test and clicking on it, I can receive this. Okay, if the distribution in here is similar to the distribution in here, then they have the same distribution, or not the same distribution, the same kind of distribution, right skewed, positively skewed, or negatively skewed, and so on. Okay, and here you have the numbers, the same numbers that we had in the Mouaz test that was done manually. Okay, I will move on to another test if that is okay.
It is.
Okay. I think I do not need to explain more. I will do it like silently, and you will tell me if what I'm doing is logical and correct. K means more than 2. Okay? Graduation, as you remember, we had 0 for not graduated, 1 for graduated, and the 3, as I remember, for semi-graduated. This is like yeah, something imaginary. However, okay, when I put it here, it tells me where do you want to start your categories. If I have 10 categories and I just want the first 3 of them, I will put 0 to 2. Okay, now I will take 0 to 3. Okay, because I remember the third group was named the 3. Okay, it is not a number, it's a name. Okay, like a numeric name. Okay, I will compare those because those are not parametric, and I will also compare those, the original data. All of this will be done in one click. Okay, do we have options? Descriptives, quartiles. Okay, let's just. Do you remember that name? when do we use this test? Well, what is the difference between graduation and uni? In graduation, I have more than 2 groups, okay? For uni, I had just 2 groups, okay? So, and what I used is K independent samples, which means...
Yeah, it's like non-parametric Anova.
Exactly, non-parametric Anova, okay. First, the descriptive statistics of each one of the 7 or 8 variables. Then, for each one of them, they distributed them to the 3 groups, the number, the mean rank. We do not need that table. What we need is this. Where is the significance for each one of our variables? Focus on the columns and on the rows, okay? You can see the rows, chi-square, df, and the significance, okay? Did we do any chi-square? No, so this chi-square is not similar to this chi-square in our minds. Okay, so what do we assume, okay? There is a significance for each one of these numbers, okay? And what does the significance? Okay, let's see here. For experience, there is a significant difference. So this significant difference is for Kruskal-Wallis test, and it is for experience. Can anybody tell me what does that mean?
Yes.
There is a difference between graduate, not graduate, and semi-graduate in experience.
Exactly, exactly. And can I say from here which one is higher than which? Okay, no.
No, it's like before we need the post-hoc or something.
Exactly, but here the post-hoc is like so complex. We already learned a lot about parametric tests, and we can I can tell you that in here you most likely need to do it by yourself. Okay, you take just the descriptive statistics for each one of them because you have the test and you have the p-value. What you need is just the descriptive statistics of each one of the groups, okay? Yes. And you can do that by splitting the file, by using crosstabs, by whatever. Is that okay? So now we learned the Mann-Whitney test and the Kruskal-Wallis test. Okay, what else do we need to do?
So just a question.
Can we delay it to the second
okay,
because like we need to finish that. Okay, non-parametric tests, independent samples, we can also take those instead of uni. I will take graduation. This is the other way to of doing the same thing. Okay, run. Okay, and you can see here the test it chooses was Kruskal-Wallis test. Then our choice was correct, and it is significant for some, not significant for some. Okay, you can see here reject the null hypothesis. Okay, let us see the okay, look, we have here for the not graduated, all of them are 6. For the semi-graduated, all of them are here. For graduated, they are distributed all over the place. So this is why it is significant. Oh no, this is not significant. Let's look at this. Okay, this is significant. We have the different distribution between each one of them. Okay, this is another one. This is another one. Okay, so we go on. What else do we need to test? Analyze, non-parametric tests, related samples. Okay, is that important? Yes. we need that. Related samples. I will say, okay, I tested for something, then I tested for the same thing, okay, and I need to compare them to each other, okay. First, I tested the, for example, interest before the course and interest after the course, okay. But let us change the names. For example, here we have interest and ability. I will make them interest and interest post. Okay. Oh, sorry. Interest and interest post. This is the meaning of a paired sample t-test. I will take the non-parametric test. We can use both ways, as you can see. Two related samples. I will take interest and interest post. Interest and interest post. Okay. What is the test type? Wilcoxon. Okay. It automatically checked this, and we need this actually. This is the test. Wilcoxon test for two samples that are paired, and here we can see the significance. Okay. Well, we used the ability to and renamed it, but okay, we are learning the concept. I have two columns, one before and one after for the same sample. We are comparing them to each other, and we have a significance. Okay. So if you want to do it in another way, analyze non-parametric related samples. Interest and interest post. Let it take it automatically, and let us see. Also reject the null hypothesis. The median of differences between interest and interest post equals 0. Okay, then I have a significant difference, but the median difference is 0. As you can see here, they are distributed, like they are different, but the median difference is not so far from each other. Okay. We can keep that for you. I will send that to the group later. Okay. What else do we need to do? We just have one thing left. Analyze. And this can't be done in both ways. This needs to be done in here. One sample. Okay. I need one sample. I will take. What do you want to take? Let's take the sum. Okay. I have a one sample, and it's not normally distributed, so I need to test in a non-parametric test. And I have something else, which is the median, not the mean. Remember that when I'm comparing it, I need to compare. We are using median in the non-parametric tests. Then I need to compare for a median of the normal population. Okay, I took the sum, but here it's not easy to give him the automatic. How can he say about the normal cutoff of the normal population? So I will customize the test, and I will compare median to hypothesized median. Hypothesized median, it means the median of the population or something like this. Okay, I will check 5, for example, and the test is Wilcoxon, as we said in the introduction. Run, and you can see here that it is different from, we checked, it was 5, and here is our difference. Okay, this is the observed median, and this is the median I put, and it is actually significant. So now I want you to think about this, and if you have any questions about this, okay, and think about, okay, I will just leave the screen like here. Okay, you can take a screenshot and you tell me about any questions you might have about these tests or the tests before. Okay, so we will meet in like 15 minutes. Okay, and those are the non-parametric tests. They are not so difficult. Okay, so see you in 10 minutes. Take the screenshot. 1, 2, and 3. I just need to tell you about, like, when we had this null hypothesis, anything that is below the null hypothesis is not a conclusion. The conclusion is in the right cell under the decision. Okay, so if we have the difference of means or of medians is 0, then okay, this is a null hypothesis, and when I have this significant result, then I reject the null hypothesis. Okay, do we have any other question before we move on to a totally different thing?
Nope.
Perfect. Okay. Here we have some data from patients and some data from controls. Okay, those are in SPSS. Okay, those data are actually for fiber density under the skin. Okay, for nerve fiber density under the skin. Okay, for some patients we have zeros. For some controls, we have zeros also in skin biopsy, and we have higher numbers and so on. Okay, that is fine. I need to compare the numbers between patients and controls. What is the test you suggest?
Two-sample t-test.
Okay, if I do a two-sample t-test, will it give me any answer? Where is the cutoff of diagnosing patients with that disease that reduces the nerve fiber density under the skin?
No.
Okay. What should I do to get the cutoff? As you remember, of course you remember from the first few lectures, we have these numbers. We have here an average. Here we have the standard error of patients. Here we have the count of patients. And here we have the opposites of them for the controls. Okay? Okay.
Yes.
I need a cutoff. Now, my aim is a cutoff. Do you remember how we did it?
Like for
Isn't it
example,
up to us? Like we usually decide this point.
Okay. So, okay, if I decide it is 0, is that okay?
no.
1.
Like not randomly, we have to accept a certain amount of error. We have to take enough specificity.
And how to do it? Do you remember the methods of doing it?
The area under the curve?
Okay, then we need a curve. And the curve, as you remember, needs points. Okay, and so what are the points? Okay, what we need to suggest first is cutoffs. We need a lot of cutoffs. Look at like I suggested all the cutoffs 0, 0.5, 1, 1.4. Okay, there might be like 0, 0.1, 0.2, 0.3. Okay, I can take the density I want. Okay, then for each cutoff, what I did is counting the patients who are under this cutoff, because as you see here, the average for the patients is lower than the average of the controls. So I am expecting the patients to be lower in than, I'm not expecting, I know that patients have less fiber density in the epidermis than the controls. So I will count the patients who are under this cutoff. Okay, and I count it with a special, it is called count if. You put the range and then you put lower than this cell. Okay, you don't need to like remember that, you just copy it from Google. Okay, I counted the patients under the cutoff because those are, tell me, true positive, true negative, false positive, false negative. Who are they?
False, no, wait, they're positive. False negative.
Are they false?
They should be positive.
Why should they be positive?
They're patients, so they're sick. Oh, your hypothesis is not about the density?
Yeah, my hypothesis is about density, but I am saying that patients have lower density than controls.
Okay.
Okay, then
so it is
where should the patients be? On the left, right?
Yes.
So if they are lower than the cutoff, are they false or right?
No, it's right.
Because they are lower.
Exactly. So it's not false, but right positive, true positive, or true negative? This cell, just tell me about this column. What does this represent? True positive or true negative? We agreed that they are
true negative.
True.
They are lower than the number we agree on.
Yeah, but my hypothesis is that patients should be lower than it is
true positive.
Okay, true positive. Don't like think about it like a fixed distribution. No, now the patients are on the left and the patients should be lower. Okay, so they are true because they are patients and they are lower than the cutoff, and they are positive, okay, because they are patients and lower than the cutoff. So true positive.
Yes.
Okay, for the second column, I collected all the controls equal to the cutoff or higher. Are they true positive or true negative, or false positive or false negative?
True negative.
True negative. Exactly. Okay, sensitivity is this number on the whole number of patients. Do you agree?
Sensitivity.
True positive on all the patients.
True positive on it. Okay.
Okay. Specificity is
True negative.
true negative on all, right? On the 70.
Right.
Okay. 1 minus specificity, I just calculated it. 1 minus this cell gives me 1 minus specificity. Right?
Mm-hmm.
Why do I need 1 minus specificity? Do you remember?
To draw the curve, to have an area under it.
Exactly. To draw the curve. And this is the curve. What I plotted in here is sensitivity and 1 minus specificity. If I measure specificity and sensitivity, what I will have is, okay, from here, from the one in here, down till here, okay? But I just want to take it to the other side, okay? It's not that important, okay? You just need to think about the closer angle to your curve, okay? If it is like this, then this is the point you need. But if it is like this is the point I need. Why is it the point I need? Because this is sensitivity, okay? And this is 1 minus specificity, okay? So for sensitivity, I need the highest point, the 1.
Yes.
For 1 minus specificity,
The lowest.
the lowest point. Why? Because it will
One
give
minus.
the highest specificity. Okay.
Yes.
So I just plotted them, 1 minus specificity and sensitivity, and I received this. What is the point I need to take? First, is it a perfect test? Do you think it is a
No.
perfect test? Yeah, not a
No.
perfect test, but it might be very good, right? Because like it is truly higher than like meaning nothing. Okay, meaning nothing means like I have this line going from 0, 0 to 1, 1. Okay, this test means nothing, but it is okay, quite higher, so it is fine. But which one should be this the point I should consider?
Maybe this one you're putting the pointer at.
Okay, we can do it easier than visually. I will just take the sensitivity and the specificity, join them together and take the highest number. Is that right?
Join them together and take the highest number.
The highest number in sensitivity will take me here. The highest number of specificity will take me here. So if they are both together so high, then I'm so close to 1.
Yeah, okay.
Okay? Do you all agree?
Like as a general rule, yes, of course. But maybe sometimes I can afford less specificity or less sensitivity, then I would just choose according to that.
Yeah, you are so right. Okay, but yeah, it's not yeah, you are right, but there are rules. For example, for my decision in here, I won't accept a specificity of lower than 60%. Okay, because the intervention is so dangerous. For example, I won't accept a specificity of lower than 90. Okay, I can define these numbers clinically, but
Exactly.
here, what I did is I joined them together. Then I took the highest number. The highest number was 1.47. Okay, where is the 1.47? Yeah, here it is.
Yes.
This is the number. I will color it. Okay, for this, I have a specificity of 84, but a sensitivity of 63. If I don't accept this sensitivity, I need to take the highest one, for example, this one. But I should know that for this, I will take the specificity lower to 0.7. Okay? We have the balance. One goes higher, the other one goes lower. Okay? So, what is the most important cell in this line, in this yellow line?
The sum of them.
No, the sum made the decision.
Okay, it is the cutoff. We are searching for the cutoff. Okay, so is it easy to find the cutoff?
Yes,
I know.
Okay, so I will show you another example. For example, here I do not have a lot of cutoffs. And here I have the ROC curve. I can calculate the area under the curve. I put just a line, and we have a mathematical procedure to calculate the area under the curve. It is not so difficult, but, and here I have the best cutoff. I took it, it was sensitivity 88%, specificity 61%. Is that clear?
Yes.
Okay.
It is.
Okay. What do we need just to get an introduction to is, okay, I just want to ask you, now we will just have an introduction about the meta-analysis, and now an introduction to specificity, sensitivity, and choosing a cutoff, ROC and AUC, and we covered all the parametric and non-parametric tests and categorical tests through SPSS. Next session, we will just do the regression and the correlation. Do you think there is anything else?
I once asked that if we want to read studies, if we can detect bias. I learned later that since I find a study on PubMed, it's probably trusted, but maybe just, no, it's not.
No, it's not. It's not. 70. I remember that the number was 70% of the studies that are published on PubMed are not going to be used, so they are going to trash. So you have this probability, 70% having a study that means nothing, and 30% this study will have a conclusion that can have any impact on the clinical aspects of medicine.
So some studies could be on PubMed but still have bias or results that I cannot trust. Is that
actually a lot of bias can be there?
Wow, okay, can I detect that? Can I know it by reading?
Let alone falsification, plagiarism, and a lot of other bad things. Yes, you can do that, and you can also find the way to do that, okay? You can just go to Google, and you will send us a report about what you get, how to assess the risk of bias, okay?
Okay.
There are many tools. You will see, okay, we have a tool to assess the risk of bias for case reports, a tool to assess the risk of bias of diagnostic studies, a tool to assess the risk of bias for RCTs, not one, but many. Okay.
Yes.
I once attended a workshop. This workshop was, do you remember the systematic reviews? Actually, our topic now is the systematic reviews. So systematic reviews use the highest level of evidence from RCTs, right? Okay. The systematic review takes those RCTs. It excluded any RCTs that has a risk of bias. Just take the best RCTs available. And out of these RCTs, they just take, they just extract the data about the most important outcomes, and they plot them together, and they give you a very good point. Like when you are gathering 10 very important and low bias RCTs, do you expect the resulting paper to be insignificant or not of high quality?
Sure not.
It might be. Okay. A training for 3 days
Why?
was just to assess the quality of evidence in systematic reviews. Okay. Even those systematic reviews need to be assessed for the quality of evidence, for the risk of bias, for everything. Okay. So if the best of the best is like susceptible to bias, to being of a low quality, of anything, okay, then we should consider how much bias we can find in a case report, or in a cohort study, or in a cross-sectional study, right?
Yes.
Okay. So I can't answer your question, Rama, with like a few minutes, while I'm telling you 3 days to assess the risk of bias of one kind of studies. Okay.
I didn't understand the last sentence.
Yeah, I said I can't answer your question about assessing the risk of bias while in just a few minutes, while we can find a training for 3 days just to assess one kind of studies for the risk of bias and for the quality of it. Okay.
Yes, that is a lot. Okay, thank you.
You are welcome. Okay, let's talk more about systematic reviews. Okay, we said they gathered data, they gathered the most important RCTs, they extracted, not here. Okay. We have a systematic review. They gathered all the RCTs, and we said that we might proceed to do a meta-analysis, we might not. Okay, so if we have this chance, we should have numbers, these numbers extracted from each study. What does these numbers mean? 10 of the patients, okay, were treated, and they were they survived. Okay, 60 of the patients were treated, but they didn't survive. Okay, 100 of the controls were treated and survived, and 100 of the controls were treated. No, they were not treated, and they didn't survive. Okay, do you know that 2x2 table? Like treatment, survival.
Mm-hmm.
Okay, or case control and survival. Okay, I had this 2x2 table from the first study, then a 2x2 table from the second study. Okay, both of them had a sample size of 200 or 300, let's say. Okay, then I had another third study, and I had this 2x2 table, but here the number of participants was 3,000, okay? 300, 3,000, okay? Here we have the RR, the RR, the RR. How can I do the meta-analysis? Here, they took the mean of the RRs. Is that good for you?
No, of course not.
Of course not. Why?
Well, the third study has thousands of patients. It cannot be compared to the first two. It shouldn't have the same value. It shouldn't have the same importance.
Okay, here we have another method. Okay, I will take all those treated, put them in the cell. I will take all those who are not treated, put them here, put them here, put them here. So I merged not the RR, but because of the reason you said, I will take the cells. Do you think this is cool?
It's not. I don't know why yet.
Because there is this an X.
تماما.
Maybe like not the same شو بيقولوا المعايير؟
Criteria.
Like
Not the same inclusion and exclusion criteria for each one of them. Not the same risk of bias. Okay, not the same age, not the same gender. Okay, so I can do that. Okay, what should I do? I use something called the weighted mean. Okay, so I have I will take the mean, but I will give each study a weight. Okay, the study with a higher sample size. Will this study have a lower weight or a higher weight, do you think?
higher.
Higher.
Higher risk of bias, lower weight or higher weight?
Lower.
Lower weight.
Okay, and so on. Okay, does that seem good?
Yes.
Okay, here you can find a meta-analysis. What does a meta-analysis look like? It looks like
This.
a forest plot. Okay, yeah, this is called a forest plot. Okay, meta-analysis can be done with gathering them without distributing the data on a forest plot, but usually when you have a meta-analysis, you will have this shape. Okay, we'll discuss it. Here we have Wood 22. So what is it? It is a study, publication year, and it has a line. Okay, so look at it. We have a line, we have a dot, and we have here a square. What does each of them mean? The line means the confidence interval. You know the confidence interval?
Yes.
Okay. The point is the mean. Do you know the mean?
Okay.
Okay.
The square. The weight.
Exactly, the weight. Okay. When you have a shorter confidence interval, do you expect the box to be bigger or smaller?
Bigger.
Why?
I have less variance.
Okay. What made you have less variance?
I'm being more strict in including like my data.
Give me another answer.
Less variance.
What is the most important thing that contributes to variance? Sample size.
Okay.
Okay. So higher sample size will give me higher weight, will give me lower variance, will give me more tight confidence interval. So more tight confidence interval equals higher weight.
Higher sample.
Okay?
Okay.
So, and you can see it here in hotter study. And the opposite can be seen in here in Mesia study. You all agree?
So in this study, I have
Questions after the.
Okay.
But do you agree?
We agree.
Okay. So goodbye. See you after the break.
Bye.
So let's start. This is how the meta-analysis, how the forest plot looks like. Okay, for each study, we have a line, the confidence interval, a box, which means the mean, weight, and the dot, which means the mean. Okay, here we have the same thing. Okay, the mean and the confidence interval. Here we have the weight. Okay, higher weight equals shortest confidence interval because of high participants, a high number of participants. Here we have low number of participants, very small weight, and very long confidence interval. Okay, so till here, they are all studies. Here we have the overall. This is the conclusion. All of them together will give me this shape. And this shape has a confidence interval, the length of the shape, and the center of the shape is the mean, the final mean. Okay? This has a weight of 100. Okay? So there are a lot of tests that can be done in here to examine the heterogeneity, meaning that, okay, if I have a study in here and a study on the right and a study on the middle, so I will have a lot of heterogeneity. Okay, if they are all homogeneous on the same side, then that would be different. Okay, and so on. Actually, it's not our one of our most important objectives. So we will just have an overlook over meta-analysis and forest plots. Okay, examples. Here you can find the first example. We have several sections, several comparisons. For each comparison, we have two studies, 4 studies, and for each one of them, I have this shape saying that, okay, merging those two together will give me this. Can anybody tell me why the confidence interval for this shape is shorter than the two studies?
Well, of course it is. It has a more important result. The sample is, it's not like a sample, but it includes both of the studies.
Okay, so why does it have like a shorter confidence interval?
The sample is
Flux
higher.
deleted all the noises and we have less variance, so it will have a wider confidence interval than the rest.
Yeah, all your answers are correct. Okay, and when you combine those 4 subcategories, you will find out that the total events are even shorter. Okay, if you remember the 3 tables, we said like we have 2 by 2 table, 2 by 2 table, and 2 by 2 table. Out of the 2 by 2 table, what is the number I can take that can summarize a 2 by 2 table? RR or 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 both? Both. Okay. What is? Tell me about something that is mutual or in common between the two numbers, the RR and the OR. What is the thing that is most important and that is like in common between these two numbers? Where do they start? Where is the point of beginning for each one of them? RR, OR, those are the basics.
Risk ratio, we have we have population with exposure, and we want to test the outcome. Odds ratio is the answer.
Yeah, what does that number mean if it is 1?
Having this factor or not is the same.
Okay, so they both start at 1. Okay, anything lower than 1 means the outcome is less probable to happen. Anything higher than 1, the outcome is more probable to happen, right?
Yes.
And this applies to OR and RR, right?
Yes.
Right.
Okay, and this should be applied here. We have the 1, we have the 1 per 1,000, and here we have 1,000. Okay, is that logical?
Yes.
Okay, because we are talking about ORs for each one of them, then the conclusion should be an OR, and the scale should be here. Okay, I want to ask you if this shape goes to the line near the 1, or if it goes like to the right, to the extreme right, or to the extreme left. What does that mean?
At 1, the factor has no effect, or
Okay, and this is why this line, you see that vertical line, this line is called the line of no effect. Any study or any conclusion that touches that line, even if not like the center is on the line, but even if this is just touching the line, the conclusion is not so important. Okay? Why? Well, we don't have anything to say. Does the intervention make the outcome more probable or less probable? No, it doesn't mean anything because it is on the line. Okay? Even if it is touching the line, the confidence interval, so if I repeat the test, okay, it can be on the other side or on the other side. Okay? So if this 95% confidence interval is just touching the line, but we don't take any conclusion. Like in here. Okay? Okay. Tell me, why is this shape different? What is the difference in here and why is it different?
Most of the data is combined in the center or near the center.
Take time, take 5 minutes to think about this, because if anybody of you knows the answer after 5 minutes, that will be amazing. Don't hurry. Look at the full chart.
Okay.
No answer?
Yes.
Yes, can you tell me?
The results of the studies, they're giving me the mean to the left of the line,
Okay.
not to the right. So the factor effect is وقائي, hold on, preventive.
Okay. Okay, that's right, but there are like more important things in the figure. Just look closely. You can find more differences. Yeah, anybody else wants to talk?
Maybe the interval is less wider, like not less wider, يعني tighter.
The confidence interval.
Yeah. No, give it more thought. Okay. I will start to give you hints. Okay.
Yes, please.
The confidence. Sorry.
The wider the interval, the
Stop thinking about the effect.
zero.
Okay, there's something here that is more important. Why?
The line of no effect. This is a 0, not a 1.
Yeah.
What does this mean?
I'm asking you.
So how are we going to divide something on other thing? The line is of no effect is 1 because the
Like we should
is 1.
we should combine it with RR 0.
Yeah, you are thinking inside the box. Okay. We are not discussing if this study is correct or if it is wrong. Okay, this is a published study, so it is correct. But there is something that you can see. What is the thing that you can see?
They are saying that the risk or the odds ratio is 0 and not 1 as what?
Give me full sentence because I don't understand anything. Okay, more hints.
Is this factor is proven to be preventive, so being 0 is not enough for us?
No. Look at the second hint.
It's a different scale.
What would you like to take?
The same as I was saying before, the wider the interval of the mean difference, the wider the interval of the mean difference, the less the figure of the
But we are not telling anything about those. Okay, just forget about them. Forget about those.
Difference between
okay. Just think about the graph. Okay, I will give you just 1 second to look at the first one. Okay. Look at this. Is that enough? Did anybody get
Okay, odds ratio and mean differences. We are not comparing the risk of something. We are comparing
No,
the two groups themselves
your
on.
screen,
ما بعرف.
your screen is not clear.
Okay.
هنيك كنا عم نقارن الodds ratio، هون عم نقارن فروق mean difference.
What does that mean?
عم نشوف إذا هدول بيشبهوا بعض أو لا. ما عم ندرس intervention بحد ذاته.
وهنيك شو كنا عم نشوف؟
intervention.
وهير
عم نشوف تأثير شيء عملناه. هون ما بعرف، كأنه عم نشوف شيء ثاني.
It's an OR, not an RR.
Is it diagnostic?
انه هون احنا عم نجمع خطوط بيانيه، هنيك كنا عم نجمع دراسات من نوع ثاني، يعني كانوا هنيك بيحملوا اودز ريشيو، هون اخذنا الخلاصه تبع الخط البياني وجمعناهم.
Okay. Make it clearer because it is correct, but you need to say it in a different way.
انه هنيك كنا عم ناخذ الاودز ريشيو، تمام.
Okay.
كنا عم نقارن الاودز ريشيو تبع اول دراسه خط اللوزن، اما هون كل دراسه الى خط بياني، فتبعا لقديش هي عم تمثل population وقديش طلعت، فعم بيكون مثلا الى نتيجه انه مثلا نحن بعاد عن المين مثلا 4، الثاني كان الى population اكبر فكان المين 3، فنحن اخذنا السيجنفكنس تبع هي والسيجنفكنس تبع هي وجمعناهم وهيك طبعا لوزنا.
Yeah. That is close to be the answer.
Yeah, هنيك كنا
the answer
نقارن OR، هنا نقارن RR.
RR and OR are compared to 1. Okay, but why are we comparing to 0 right here?
زيرو when يعني وقت بناخذ زيرو نحن بنقبل النول هايبوثيسز، فهون نحن عم نشوف انه هل نحن وقت جمعنا هدول الدراستين او جمعنا النتيجه تبعهم نحن رجعنا للنول هايبوثيسز ولا ما دخل.
The difference is so simple and the answer was in the first lecture. Those in the odds ratio or in the relative risk, we have dichotomous data, yes and no. Here, we have continuous data.
Continuous data.
That is the difference. That should be clear to you. Why? Because we have mean. Here, the word mean, and there, the word odds ratio. Okay? That should give you a different reflection in your mind. Okay? You should understand that we are talking about totally different thing. Okay? Here, the first study said that the mean difference between two things, okay, between the controls and the cases is -3. Okay, the cases are lower in 3. The second study, the cases are lower in 2.2. Okay, here they do not say that. They say, okay, 50% of the cases died. 20% of the controls died. Okay, so we have a relative risk. Okay, do you understand the answer in here?
Yes.
Okay, but why is it 0 here? Because 0 in here means that the cases and the controls
the value
have no difference. Okay?
Okay.
The line of no effect here means that there is no difference. That means 0. Okay? We can't have a minus. I just put here a lot of lines under the minus. We can't have a minus for an odds ratio, right?
Yes, of course.
Okay, so this is the answer. Okay, just look closer. Okay, always keep that on your mind. What do we have? What are the data?
Yeah.
What are we saying about what? Okay. Okay, this is another program. This program is called a reference manager, and we don't need this anymore. Okay, for the reference manager, we will just try to build a very simple odds ratio forest plot. Okay, I have an intervention review. This intervention is called DD for a problem, a full review, finish. Okay, well, we write systematic reviews in this program. Okay, so here we have data and analysis. Let's talk about the tables. Add the study. The study is called DD. Finish. Okay, here we have a study, and this study is empty. Okay, then we need to add another study. It's called EE. Okay, when I want to compare or have an outcome, I need to have more than one study. Okay, so I have 3 included studies. Somebody is talking. Okay. Here we have a comparison. This is the first comparison. For this comparison, add outcome. The outcome here you can find dichotomous or continuous. Okay, we will just take dichotomous as an easier way to do it right now. Okay, dichotomous. Do you know that table?
2 by 2 table.
Okay, we have experimental and controls. Okay, we have total events. Okay, then I have, for example, for experimental, 5 of them. Add study data. DD RR E. Okay. How many events happened in here? 5. Total 10. In the controls, it just happened in 2 out of 10. Okay, in here, and you can see it in here. This is a forest plot. I have this difference, this confidence interval, this weight. It will give it the weight, the that applies to such a sample size. And you will see that and how it will contribute when I have, for example, in here, 300 or 300 out of 1000, and the controls, let's say 100 out of 1000. Okay, you see that the weight that was going to the first study just went smaller because the second study is so big. Okay.
Mm-hmm.
I will add here, for example, 4,000 out of 10,000, and here 6. I will put this study on the other way of the line, okay? You see, the third study, because it is bigger, but it has like a very high weight, it took the outcome, the total, to its side. Also, I had very good studies on the other side, okay? But the weight that was allocated to them went really small because of the weight of this study. Okay?
Yes.
Are you satisfied with like this brief introduction to meta-analysis?
Yeah.
Yes.
Okay.
Yes, it was great.
Then do you have any questions?
How can we download this application? How can we download this program?
Yeah, it's available for free, I think. Okay, I will send it to the group.
Okay.
I have a question, but not about meta-analysis.
Yeah, please.
Okay. How do is there people who like see the analysis we do before we publish the paper?
What
is the like I have a data and I analyzed it, okay, and I'm writing my paper. شلون بيقرروا إنه الاناليسيس معمول صح؟
there are some clues that they can find that you have like ruined your data, but most of the times you can do it, and they won't take the whole sheet of data you have and do the analysis again, okay? But if there is something so obvious, they will highlight that and tell you that your analysis is not correct, but they won't do the analysis again and make sure that you are right, okay?
Okay.
Yeah, but for very high rank study, very high rank journals, you need to send the whole data with your submission. Okay, then
thank you.
صحة طارق شهيان. See you in the last on Thursday.
Thank you.
Hello. Goodbye.
Bye.
Goodbye.